All right, very good morning to all of you. Previous session we were discussing SCR, the main workhorse of the power devices or the head of the thyristor family. That is the way we name the SCR. We found that structurally it had 4 layers, PN layer was there, and then as usual in all power devices the N- drift layer was responsible for the very large voltage blocking capability. We were in a position to understand the turn on process or how that positive or regenerative mechanism is happening when a very small gate pulse of sufficient amplitude and time duration is applied. So that we used a 2-transistor analogy model of an SCR to understand the regenerative process. So that was regarding the previous session. In this session, we will take up the VI characteristics of an SCR, and then we will see why providing a negative gate pulse will not turn off the SCR. That is important. And then the transient characteristics, they are very similar to that of a diode. Both the forward and reverse bias turn on and turn off transients, they are very similar to that of a diode. So with that, SCR will come to an end. With this session, I will be able to complete the details regarding SCR. On that note, I'll start sharing my screen, and then I'll start discussing the VI characteristics of an SCR, followed by the importance of turning off, or how do we turn off the SCR. These are the main objectives that will be covered in this session. Okay, so I hope my screen is also visible. Today, as I said, it will be turned VI characteristics of an SCR. And let us discuss the turn off process. What is the turn off mechanism that is happening inside the SCR, so that the negative gate pulse will not be in a position to turn off the SCR. It is very, very important. We'll try to understand both in today's session. Now, VI characteristics goes like this. Please remember, SCR is one main power device which is capable of handling both the forward voltage and the reverse voltage. Handling here means blocking. So SCR can block the forward voltage and reverse voltage. In fact, in all SCRs, practically the forward blocking voltage level and the reverse blocking voltage level will be similar, which means the VI characteristics, they are going to be symmetrical, the forward and the reverse bias characteristics. But forward bias characteristics are even more important, and they are quite interesting as well. Anode current obviously will be plotted along the y-axis, while the anode to cathode voltage will be plotted along the x-axis. First, let us take up the forward bias characteristics, which will be in the first quadrant. Now, the characteristics goes like this. There will be a particular value of forward anode to cathode voltage till which the SCR will not conduct, which means anode current is going to be 0. Now that voltage is called as VFBO. This means forward break over voltage. So the SCR is able to block a particular magnitude of forward voltage without applying any gate pulse, no gate pulse. That is actually, that will be the maximum forward blocking voltage capability. In case you can, in fact, you can name this as VFBO suffix max or suffix m. You can understand it that way. The maximum forward voltage which the SCR can block. And when you apply a gate pulse, as we had seen in the previous session, the SCR starts to conduct as soon as it receives a forward gate pulse, and suddenly the SCR is going to be turned on. Get on with the turned on, and then there will be current that is going to flow through the SCR. I am drawing this certain profile in the dotted region, because that is where the SCR is going to be very much unstable. The dotted lines, they are referring to the case that the SCR is unstable, right? And the particular magnitude of anode current at which the SCR just begins to conduct, that voltage, sorry, that current is called as latching current. IL is latching current. I will write the definition of latching current a little while later. And this is for a particular value of gate pulse. I will call it as, I have indicated as IG1, but you can refer that to as VG1 also. A particular value of gate voltage, it will cause a gate current. Because I know that SCR is a current control device and I have explained that to you in the previous session, I am taking that liberty to write IG1. Now, if you increase the gate voltage, magnitude of gate charge carriers that are injected, it means that the SCR will be able to conduct earlier. So it will be able to conduct sooner. Let's say this will be the characteristics for, I'll use another color. So, okay, fine. So I think I'm muted now. Yes. So when we increase the gate current, the SCR begins to conduct earlier. Breakover happens earlier. Similarly, when you further increase, quite obviously, it will start to conduct, it will begin to conduct even earlier, IG3. So the relation is, it is like this. When IG1 is less than IG3, sorry, IG2, this is less than the third gate current IG3. So this is the relation with regards to the gate currents. And IL is the latching current value. Once the SCR starts to conduct, it will carry the complete load current. So the current through the anode, so this portion will be the anode current. SCR keeps carrying the current that is demanded by the load. When the SCR again begins to conduct, the voltage drop that is developed across the SCR will be less. Okay, that you can see. You can actually drop a line over here, and then you will see that the voltage drop across the device will be less, across the SCR in this case will be less. This is the forward characteristics. Now I should write two important points. Number one, when the SCR is not conducting, but still a forward voltage is applied, that is, when we forward bias the anode and cathode terminal, it will be blocking the forward voltage, but it won't conduct. That state is called as forward blocking state. Very, very important. This is unique feature of an SCR. Forward blocking state. You won't find this in other devices. It means SCR does not conduct no gate pulse is supplied, but anode to cathode is forward biased. This is what is called as forward blocking state. So it would mean this region, this portion of the characteristics before the dotted line till this point. You call that as forward blocking state. One point. Another point is latching current. Latching current. The actual definition is minimum anode current that is required to maintain the SCR in the on state even after removing the gate pulse, or just after removing the gate pulse. You can put just after because we have used minimum. So, I mean minimum anode current that we have already used. So you can put just after removing the gate pulse or immediately, which means you can recollect this with the previous session. I told that latching current was the point that I was discussing. The explanation is the minimum value of anode current that is required to maintain the SCR in the on state just after removing the gate pulse. That is the definition of latching current. The explanation is for the positive feedback mechanism to start, we need a gate pulse of sufficient amplitude and time duration. Now, once that positive feedback mechanism starts, gate pulse can be removed. Now, the amount of current that flows through the anode, magnitude of current that flows through the anode for setting up, for just commencing that positive feedback mechanism, that current is latching current. This is the explanation. All right. Now, there is one more current which will be used for turn off. That also I will mark in the characteristics. Probably I will use another color which is slightly less than this. So that current is called as holding current. I will write it here. IH is holding current. That is, if you want to turn off the SCR, you have to bring the anode current below the holding current value. That is the only way to turn off the SCR. Meaning, positive gate pulse, positive anode cathode voltage will turn on the SCR, but negative gate pulse will not turn off the SCR. Okay. We will see in a little while from now, why that gate loses its control. But before that, I will write what is holding current. Then I will pass on to the process or the importance of negative gate current and how that can be avoided. Holding current is minimum anode current below which the SCR turns off. Okay, so I will scroll up and show the characteristics again. The important points are forward breakover voltage without any gate pulse. That is the maximum forward breakover voltage. And when we don't apply a gate pulse but still forward bias the SCR, the device or the SCR will remain in forward blocking state. The hashed portion in the VI characteristics in the forward bias first quadrant, that will be forward blocking state. Second point. Third point, the moment a positive gate pulse of sufficient amplitude and time duration is applied, the SCR turns on immediately. Very short, in very short duration of time, the SCR turns on. Therefore, the travel from voltage to the latching current value is actually non-linear. You can't predict the path that the SCR is going to take. That is non-linear. Therefore, it is marked as dotted line. The regenerative mechanism sets in at a minimum value of anode current, which is termed as latching current. So once latching current is reached, gate pulse is not required. Gate loses its control. That is the third point. Fourth point is holding current. The minimum value of anode current below which the SCR is going to be turned off. So if you want to turn off the SCR, anode current must be brought down to holding current or zero, below the holding current value or zero, because holding current magnitude will be very, very less, 5 milliamps, 7 milliamps, etc. Right? Which is practically zero. 7 milliamps, yes, it is a number, but then the SCR current rating will be in tens and hundreds of amperes. So you compare with hundreds of amperes, and then when you compare 10 milliampere, it's nothing. It is not even similar to an ant biting an elephant. You can't even imagine that. Or if you want to understand that slightly better, yes, you can imagine holding current to be an ant and the actual current rating 100 ampere to be an elephant. I mean, a fully grown elephant. Don't think an elephant calf. So an ant biting a grown elephant is nothing. That is holding current for you. Okay, 10 milliamperes for 100 ampere SCR. So if you want to turn off the SCR, understand this way, bring down the anode current to 0. You understand this way, but when you tell it technically, it should be less than the holding current value. Now, how do you bring that current to 0? You have to reverse bias the SCR, reverse bias the anode cathode terminal, wait for some time, only then the current can be brought down to 0. And it has to regain its reverse blocking capability. Fine. That is the process. Because I said reverse blocking capability, I will draw the reverse characteristics and then I'll wait for some more time. I mean, I'll give you some time to pose some of your questions. So the reverse characteristics is going to be very similar to that of the forward bias characteristics. When we reverse bias the anode cathode, the SCR is going to be reverse biased. There will be a maximum voltage below which the SCR is going to be damaged. It is called as, I will write this as VRWM, which refers to VRWM is maximum reverse working voltage. Which means this is the maximum reverse voltage that the SCR can withstand. Above this, if you increase the reverse voltage, it will give way, it will get damaged. Fine. So these are the VI characteristics, significant points with regards to the VI characteristics of an SCR. Fine. Then I will now pass on to the turn off. Okay, I will tell something about turn on mechanism that is called as gate triggering mechanism, or how do we turn on the SCR? It is called as gate triggering. First experiment, in fact, we did in lab, that was with regards to the triggering part. I told R triggering, RC triggering and other things. I had demonstrated using a kit as well. That comes under gate triggering circuits. Now, why do we need this gate triggering? This is required to provide the, I will write IG, that means to provide the required gate pulse to the SCR at the desired instant with a definite amplitude. That is the requirement. Required to provide IG, gate pulse to the SCR. Now, how can we trigger the SCRs? If not by gate pulses, how can we trigger the SCR? The methods are, one is you can actually keep increasing the rate of change of voltage, dV by dt. It is called as dV by dt triggering, which means you keep increasing, not the magnitude, keep increasing the rate of change of VAK, anode voltage. Okay, just keep changing the rate at which you increase VAK, not the magnitude. I hope you understand the magnitude. See, 0 to 100 amperes you can increase in 10 minutes, and 0 to 100 amperes you can cause that increase in 1 minute. So 1 minute will have a higher dV by dt. So that will cause that injection of charge carriers inside the layers, and then that will cause the triggering mechanism. Positive feedback will set in and SCR gets into on state. That is dV by dt triggering. It is not advisable because sometimes the device may get damaged. I should write this in red. I will do that because it is not advisable. Better to write in some different color. One method. There are some SCRs which are called as light activated SCRs. They are light activated SCRs. They are in short written as LASCR. So they will be triggered using light. Light triggering, optical light, right? So that is light. And then thermal triggering is also there. Again, not advisable. Thermally triggered. So thermal triggering is there. Again, not advisable. Because please understand, all the semiconductor devices, irrespective of power level, they suffer from, they are very, very vulnerable to thermal runaway problem that is happening. See, all the devices, there are charge carriers. The more the amount of charge carriers that are liberated, free charge carriers, the more the conduction is going to be. And please understand, all are semiconductor devices. So when temperature of the layer is increased, more amount of free charge carriers will be available, because that heat will provide that required energy level to move from the valence band to conduction band. Right? Therefore, as temperature increases, free charge carriers will increase. When free charge carriers increase, current increases. When current increases, that will further increase the temperature. So that is going to be another regenerative process. That is how the device breaks down. It is like this. Temperature increases, free charge carriers will increase. When free charge carriers increase, current will increase. Increment in current, will further cause increment in temperature. That is the chain reaction. All right. So in between, that is the process that is happening. Because of temperature, the device will break down. Fine, statement is true. But how is it breaking down? Why is it breaking down? Because of more free charge carriers, consequent increment in current, resultant increment in further increment in temperature. That's all. That is the process. So thermal runaway problem has to be avoided. As a result, thermal triggering is also not preferred, not advisable, or preferred. Okay, very good. One more wonderful thing is called as di by dt triggering. You need to understand this very, very clearly. Di by dt triggering. Again, not preferred. I'll tell you what is di by dt. Before that, I'll ask you a question. Have you played with a sheet of paper and tried to handle that, place that sheet of paper over a candle? Have you ever done this in your childhood days? You are still children, not unlike me. But have you done this, or have you seen somebody doing? Imagine a candle flame and imagine one sheet of paper. You try to hold it by two hands. Process which happens in di by dt triggering. Now that black color thing which we were discussing, I hope you had understood. Therefore, I am writing that. It is called as a hot spot. Not our mobile hotspot, but that spot will be really hot. Quite literally, it will be really hot. Okay, this is what happens in di by dt triggering. The meaning is, now in SCR terms, or okay, first let us discuss this paper. Now in paper, the spot becomes brown because that spot alone is subjected to more heat. Okay, now corollary, or rather the analogy, in SCR, one spot, one region of the SCR, the flash carriers more heat, then it turns to a hotspot. di by dt triggering, this is what happens. Di by dt means you are flushing in more, you are injecting a lot of electrons, lot of charge carriers within a very short time. You are injecting a lot of electrons within very short time. So those electrons will not have any place to go, get accumulated in one spot. That is going to create this hotspot. So in hotspot, accumulation of charges, that is causing hotspot. Remember, di by dt is very, very, very dangerous. That is, you can't allow the current through the SCR to increase arbitrarily. Within a fraction of a second, don't allow the current to increase. It won't withstand. The device will not withstand. It will get damaged, just like your paper. Best way of triggering is provide a positive gate pulse of sufficient amplitude. Is to provide gate pulse of sufficient and communication. There are some more points that need to be covered. Now, the important point that I wanted to mention, I mentioned that in today's, the beginning of today's session as well. The gate is going to lose its control once the SCR turns off, which means if you want to turn off the SCR, once the device turns on, sorry. Gate. See, gate is going to be located in one corner of the entire structure. Therefore, gate cannot have control over a majority of the cathode layer. That is the reason. In fact, you can understand this from the two transistor analogy as well. If you remove the base of transistor T2, the NPN transistor, still there will be collector current that will be acting as base current to transistor T2. You can refer to the two transistor analogy for better understanding. Now, the example that is explained, the explanation that is given in Joseph Vidyathil, it explains di by dt and the location of gate better in one shot. So you try to refer to that text, Joseph Vidyathil. Right. This is just for your reference, understanding purpose. Of course, I have noted down the reason why the gate is going to lose its control. The reason is it is located far away from the majority of a cathode layer. Fine. There are 2 points, and then I'll stop with those 2 points. One point is, what is the remedy? Suppose you want to have a device which is going to turn on the device and turn off the device by a gate pulse. What is the remedy? The remedy, what should you do? The answer lies in locating the gate centrally. When you locate the gate at the center, then it will have control over the entire cathode layer, which means you apply a forward gate pulse, positive gate pulse, device turns on. You apply a negative gate pulse, device turns off. That is possible. Such a device is called as gate turn off SCR or GTOs. Sorry. GTOs. GTO. Gate turn off SCR. So GTO. This means negative gate pulse turns off the SCR. Fine. So for this to happen, how should the gate be located? It should be centrally located. Gate is centrally located. Thank you.